afternoon session for this Raychaudhuri 100th birth anniversary event. Thanks a lot, Bryan, for having accepted our invitation. You're currently muted.
Oh.
Okay. Yes, right now. Okay, perfect. So we can see your sharing screen. Let me just introduce you. You're joining us from Italy right now, right?
No, I'm Honduras. Sorry for...
Okay, no problem. So anyway, you're professor at the Universidad Nacional de Honduras, and you've done your PhD in Mexico, Puebla, a postdoc in MCTP. You also visit the ICTP in Italy, so your background is quite extensive. And today you're going to talk to us about perturbative quantum gravity beyond Hilbert-Einstein action. Once again, thanks you a lot. And as soon as you're ready, please.
Can you see my screen?
Yes, we can.
Okay, thank you very much to the organizer for giving me the opportunity to present this work here. It's really a tremendous honor to be in this symposium, in honor to Professor Raychaudhuri. I'm going to talk about, as you say, about perturbative quantum gravity from the so-called modern perspective, using scattering amplitude, all the modern techniques that has appeared in the last, let me say, 20 years in the scattering amplitude projects. I'm going to tell something that is going beyond the Hilbert-Einstein. This work is in collaboration with amazing people from Mexico, like Lorenzo Diaz-Cruz and Ana Avilés from Puebla, and Alan Alonso, that at the time was in the ICTP, and now he's at Mexico City in his PhD. He was my student 3 years ago. So let me start. I'm going to start with a little bit the motivation from the quantum field theory point of view. I'm going to talk about the spin or helicity amplitude for massless and as well for massive particles. And then I will make the connection with black hole physics and for sure with general relativity and perturbative quantum gravity. I will show some examples, and then I will show some new results that will be published in this month. Okay. As you probably know, scattering experiments are very crucial to understand the fundamental blocks in nature. For example, the standard model of elementary particle was developed largely because the scattering experiments. It's very well known that from the theoretical point of view and also from the experiments that quantum field theory describes the fundamental force and all the interactions of nature. In this case, the differential cross-section that is computed with quantum field theory techniques made the connection between the theory and the experiments. So as in quantum mechanics, for example, the density probability is proportional to the model square of the wave function. Here in quantum field theory, the differential cross-section is proportional to the square of the amplitude. So the amplitude becomes the building block of this business. Okay, so people from the experiment has a huge amount of data. This data need an interpretation that comes from the theoretical prediction, and that's why we need to compute the scattering cross section. Okay, typically we use the techniques from the classical quantum field theory books. We have a classical Lagrangian, then we quantize, we obtain some Feynman rules, we build the amplitudes, then we using, of course, all these Feynman diagrams, and then we square this amplitude, and we have the differential cross-section that, as I said, is made the connection with the data and the theoretical prediction. Almost 30 years ago, we had these amazing results from Parke and Taylor. For example, if you want to compute the collision of two, let me say, gluons, and you have, for example, three gluons in the final state, you need to take into account 25 Feynman diagrams. And so this, if you make this computation, you need for sure high performance computing. And just to show you part of the result, the total result, 25-page result, is a huge, amazing result. But using these new techniques that Parke and Taylor found in the 80s, we only need to compute using the spin-orlicity formulas this very short result, as you can see here in the bottom of the screen. So this is for massless particles, for sure for Young-Mills theory. We would like to know if these techniques could also be useful for massive particles, and I will show you at the end of the talk that these techniques are also very, very, very natural to implement in quantum gravity. Okay, so the main idea here in the spin-orlicity formula is to connect the building blocks here in quantum field theory, the amplitudes in terms of the external data. The external data is in this case the energy and the three momenta. So basically, we write our amplitude in terms of the spinor, Dirac spinor or Wells spinor, in terms of this external data. We use this nice variables with brackets. For example, here P and K represent the label of the particle, the four momenta that, as you know, the component is the energy and the three momenta. In this case, when you use this change of variables, or these new spinor variables, the magic appears when you replace the traditional Feynman rules in terms of this notation. Let me say, so for example, you want to make some calculation in quantum electrodynamics, you need the Dirac spinor and as well the solution of the Maxwell equation. Notice here that from the beginning, you start with 2 degrees of freedom for the photon. And you don't need to use gauge redundance in order to obtain the physical degree of freedom. From the beginning, you start with the 2 polarization vectors. So that's also is very nice. And in order to build and compute the amplitude, I will show you an example after this. You only need to use these rules. For example, the first one here is antisymmetric of the brackets, and also you can see in the last rule here in the left that you obtain a Mandelstam kind of variables very quickly, and this is fine because we want to obtain our result in terms of the data. And also, for example, you can express momentum conservation in terms of all these brackets, S square and angular brackets, very very easy. It's better than use trace technology that appear in the traditional quantum field theory books. So how this work? We are still recycling the Feynman techniques. We start with the Lagrangian, we quantize, and we use Feynman rules, Feynman diagrams. But here we in this case we implement in this step. For example, when you have the amplitude, we use these spinor variables. So here's when the magic appears. Let me show you an example. For example, consider the annihilation of matter and antimatter. In this case, two leptons, electron and positron, and you obtain two quarks and one gluon in the final state. So this you have, in order to make this calculation, we need to take into account two Feynman diagrams, and this one that I am showing here. You build the amplitude using the traditional Feynman rules, and the final results, after implement the spinor variable, this very compact formula. Let me show you how you react to this, how we get this final result. Let me show you. For example, you build the amplitude using Feynman rule, then you translate or use the new spinor variables and in the amplitude, and use then the rules that I already showed you, and you can see that you obtain all these bracket products, square and angular, that are invariant, of course, from Lorentz transformation, all of that. But it's very nice because you can see how this product cancel each other, and you obtain. So if you need to do this calculation, it's better to use this spinor licit formalist than the trace for sure. And we want to. This is just an example. Let me show you something more advanced. Let me say, for example, for the massive case, we already have the Feynman rules in this setup. For sure, we need to incorporate a new degree of freedom for the vector field, because we want to take into account the mass. But still, the same rules that we use in the massless case are still useful here. So let me show you one example. For example, if you want to compute the Higgs decay to body, to fermions in the final state, we build the amplitude using traditional Feynman rules. Once you have this amplitude, then you implement the spinor helicity formalist, and you obtain two helicity amplitude. Very simple, very compact expression. You can see here that even without square the amplitude, you already obtained the mathematical expression in terms of the external data. You can see here in the for example, in this problem, just in very few steps. Okay, let me show you another more involved calculation. For example, the mu on the K to 3 body. Again, you build the amplitude using Feynman rules. Okay. But once you have the amplitude, you implement the spinor helicity formalist. Here you found 4 helicity amplitude, but it's very simple to see which amplitude doesn't contribute to the amplitude in the sense that we already know which of these products is 0. It's very quickly. I will not go into the details. I'm just showing you this in order to see that the spinor helicity formalist is very useful even when you take into account the mass of the particle. Okay, you can go even with these techniques to supergravity in order to compute any cross section or width decay that you want, taking into account, for example, gravitino, the superpower of the graviton. we already have the Feynman rules in terms of these spinor variables, so we are able to make this difficult calculation. For example, if you want to compute the decay of some massive, very massive scalar particles in these SUSY models that decay into 3 particles, where one of these particles is the gravitino. The gravitino is very complicated, or let me say in another way, made the calculations complicated because it's 3/2 spin particle, and this is very difficult to calculate. This calculation is using trace technology or the traditional quantum field theory approach. And you can see that this is just a part of the total result. It's like 10 pages of the result, but using these spinor techniques, you can see again that the result is very compact and more, it's very clean calculation. So the spinor-licity formula is really a scattering amplitude in quantum field theory. I know that this is a symposium related with gravity, but in the last part of my talk, I'm going to use these techniques in order to calculate, for example, gravity amplitudes. And once you have the gravity amplitude, you are able, for example, to unless you are for example, the potential are. So now we have, as all of you know, a new window to explore the nature. We have gravitational wave. We have more precision in the picture of the black holes. We also have a huge amount of data that comes from LIGO and Virgo. And in the case of a binary black hole system, and this data needs to be interpreted, and people are trying to compute correction to the Newton potential, and some people like Hilbert and other people from France are using this quantum field theory techniques in order to find this correction to the Newton potential. So this is a kind of motivation. Okay, let me start this part of the talk from where I'm going to talk about perturbative gravity. This starts for sure with Einstein, and then with Bohr trying to implement the Heisenberg uncertainty principle to gravitational radiation, and of course then Bryce DeWitt and Wheeler comes to the action, but the part that I'm most interested is in this, when Feynman and Bellman also compute some quantum gravity calculation using the Feynman traditional approach. Then appears in theory, the amplitude project, perturbative duality, and for sure we are waiting for more outstanding results from the amplitude project. But the essence here is that any theory of quantum gravity, there exists a particle called the graviton, spin 2 particle, which is a quantum of gravity, just like the photon is the quantum of light. This is the main point here. Okay, so let me talk a little bit about the Hilbert Einstein from the perturbative quantum gravity point of view. We will follow this in this scenario, the same approach of perturbative quantum field theory. Okay, so we already know that the Einstein equation of motion are obtained from the following action, the Hilbert action. We are using this convention, and in this case, the metric play the role of the field, and we will expand the metrics or what people do is expand the metric until first order in kappa, and then they replace this metric in the Hilbert Einstein, and we obtain infinite terms. For sure, in this linearization of general relativity, let's say we already know that the polarization tensor in gravity are proportional to the product of the two polarization vector. We are using the standard gauge, the Donder gauge here. But something that you can notice here is that we already know these two guys, these two polarization vectors, we are able to write them in terms of the spin-off variable. So this is very nice, okay? Okay. Probably all of you know this beautiful paper from Bryce DeWitt from the 60s. He computed the scattering of in pure gravity of two gravitons to two gravitons, a four-body problem. This is the vertex of this using canonical quantization. So you can see that just with the vertex you can see that the calculation will be very, very, very messy, very difficult. Okay, but the final result of the cross section, is very simple. That's why the Bryce DeWitt said a large amount of cancellation between terms still has to be done of the algebra, and this combined with the fact that the final result is ridiculously simple leads to believe that there must be an easier way. Okay, we already know that there is an easy way to calculate this scattering process. Just let me see as an interlude some perturbative jewels. For example, we already know how to calculate in Yang-Mills theory the 3-point vertex or 3-point function. For example, that comes from this Feynman diagram with 3 gluons. It's a very simple result using spinor helicity. That is the Parquet-Taylor result. And if we want to know, for example, using scattering amplitude, the result of 2 gravitons to 2 gravitons, we can use recursion relation using the Parquet-Taylor results. Just it's very easy or very fast to calculate this recursion relation. That the main idea is calculate scattering amplitude with higher number of particles in terms of scattering amplitude with lower number of particles. Okay, so in this case, starting with the 3 points Parquet-Taylor amplitude, you can obtain the 4 points amplitude using BCFW recursion relation. This is just for Yang-Mills, but we also know this beautiful result from string theory that at least at 4 points, gravity amplitude, pure gravity amplitude is the square of 4-point Yang-Mills amplitude. So you calculate gluon's amplitude, you obtain by free graviton amplitude, just squaring the Yang-Mills. So this is really amazing. For sure, this is in the literature. This is for massless particle. And but still is a great result. Okay, let me show you what about a little bit about my work. What about the interaction of the graviton with massive particle, scalar, fermion, any scenario that you can imagine? For example, if these techniques also are useful, or you need to implement new techniques, so let me explore this scenario. For example, the correction of the energy of the graviton at one look, the scattering amplitude is this one this result. And if you have to impose, for example, war identity, and this war identity constrain these functions that are okay, this F1 to F5 that are connected with the structure of the loop. This result is already published by Pilapsis from Munich, but we want to see if this scattering also admit this double copy philosophy or connection. This is the amplitude, the green one from quantum gravity. We will explore just the 0-0 component using this Minkowski signature, and we see that at least with all the 0 component in this polarized amplitude, we obtain some kind of double copy. You can see here the energy square plus the quadrum momentum to the square comes 2 times. So this is good, at least at least at this 0 component. We already know from textbooks, for example, from Peskin, also the amplitude for pure from the correction of the gluon at what loop with the fermion in the loop, and we see that the 0 component is at least the kinematic term, the square root of the gravity. So this is nice, but we want to know if this also is true with the full result. But this was a kind of check. Okay. Okay, but you can see here when we calculate the total result for the graviton. This is the total result for the graviton, and this is the total result for the photon or for the gluon. It doesn't. Okay, and you can see that if we squared the photon or gluon amplitude, we obtain, after permutation of the index, the same result. So we have double copy even when the graviton interact with massive particle. This is nice. Okay, so with this at hand, you can calculate, for example, the decay to one massive scalar could be the inflaton, the dilaton, or why not the Higgs. When the Higgs, for example, interact at one loop with the fermion and then decay to 2 graviton. We are able to do this calculation now using the low energy theorem. This is another technique from quantum field theory that you can calculate, for example, at least when the Higgs is a low energy, from this Feynman diagram without the Higgs, this relation exists. Okay, so we are able to calculate this amplitude, and we can calculate also the width decay. Okay, if you, for example, if you don't know, for example, imagine a scenario when you don't know the spin or helicity formalism and you want to make this calculation, you need to use trace technology, just the traditional textbook techniques. But this is not the result. It's just the square amplitude. You need to calculate all this product. This could be very, very involved. But, for example, if you remember the spin or helicity formalism, you can write this polarization tensor in quantum gravity in terms of the product of 2 polarization vector, and then if you remember the polarization vector in the spin or helicity formalism, basically you are done. This is, for example, all the possible spin or helicity configuration in this case, and you need to remember, as I said, only these basic rules for the 2 polarization, and in this case, the not vanished helicity amplitude are only this one. 2 plus, and also the complex conjugate. You only need to calculate one, and then you, because are almost the same when you square the two results because of this. And in this case, only in 2 steps you obtain the final result. So you can see that even when you have quantum gravity coupled to matter, the spin-orlicity formulas is very useful and reduce a huge amount of work. And this is really amazing. Okay, so at the end of the story, you have, for example, I know that it's very difficult to see the connection at the level of the Lagrangian, because here you have gauge symmetry, here you have reparametrization symmetry. At the level of the amplitude, in the language of Feynman, it's still not clear how to see the double copy. But when you calculate the scattering amplitude, it's very directly that you can see that, for example, here at the left side, I have the Young Mills, and the green box are the gravity. You can see here that the gravity is just the square of the Young Mills. So this is really amazing, and this still works even matter. Okay, but what about going beyond Einstein-Hilbert action? Okay, we have studied the coupling of scalar particles with gravitons within the context of perturbative gravity. Okay, but we would like to explore more. In other words, complex interaction, specific decay processes, extended gravity action, and theoretical connection. But in order to do this, it's necessary to go beyond the minimal and linearized approximation. So this, one of our goals was to identify possible difference in the contribution coming from quadratic terms involving the Ricci and the Riemann tensor, for example. Okay. In this case, so we are considering an expansion to the metric up to second order in kappa. Okay, so let me show you how this works. So we need to expand the metric spheres. You can see here in the right side up to second order in kappa. Then we need to evaluate the Christoffel symbols. Okay, we do that up to second order in kappa, and then we need to calculate first the Riemann tensor. We are okay, and then we compute the Ricci tensor again to second order in kappa, and finally the scalar curvature. With this at hand, we are able, for example, to calculate the second order 3-point interaction. Okay. In the left side, I have the vertex in terms of the coordinates, and in the right side in terms of the momentum space. Okay. For example, the terms that the second order term that comes from the Ricci scalar is this one. We calculate also the term of the Ricci tensor. Okay, we already have all the calculation. See, it's not easy. We are looking for terms that respect a kind of double copy, as I already showed you, but it's not easy to see that here because we are still off shell. Okay. But once we calculate the scattering helicity amplitude term by term, for example, up to second order, you will see that, for example, the traditional interaction of Ricci with the scalar field doesn't contribute. Neither the square scalar Ricci, neither the Ricci tensor, but the Riemann square term contribute. Okay, this is really amazing because we again obtain very compact and simple terms. Just to show you, if you, for example, how this calculation goes, for example, you have to take into account all these Levi-Civita in 4-dimension products. So it's not so easy, okay? But for example, this was using this Lagrangian here in the orange box, with taking into account, for example, the interaction of this square tensor with the scalar field. But for example, using the scattering amplitude techniques directly from the so-called bootstrap project, where using, for example, the little group techniques, you already have these formulas where H1, H2, H3 represent the helicity of particle 1, 2, and 3. And for example, in this case, the 3-point interaction with 2 gravitons and 1 scalar, you already know the spin of the particle. For example, the graviton is spin 2, and the scalar is spin 1. So you already obtain this result. So very easy, very fast. And you can see that it's the same result that we already obtained using the Lagrangian. So it was really nice. We already know this result also from Young Mills, and you can see that here the double copy against appear. Okay. So I'm almost done. Let me say some final comments. We have seen that the spinor helicity formula is very useful to evaluate scattering amplitude in quantum field theory, but as well in perturbative gravity. Even considering quadratic terms in the action, the Ricci, the Riemann terms, and second-order terms in the metric field expansion, we found that the vertex satisfies double copy relation. KLT is from Kawai-Lewallen-Tide, that the people who made this connection from string theory in the 80s. So the inclusion of the square Ricci and Riemann terms in the metric expansion opens, at least for us, a rich landscape of physical possibility ranging from new interaction vertices and experimental signature to insight into gravity beyond general relativity and connection to other theoretical frameworks. So thank you very much for your attention.
Thank you, Ryan. Thank you for the really interesting talk. So is there any question?
Maybe I'll start with some basic questions I have. Thank you, Bryan, for a very clear talk. I have maybe very basic questions, like all the signs you had for lambdas, minus, plus, plus, and all these things. These are coming from the rules you had for your spinners, right? For these 4 momentum spinners, which you converted in this formula. So these are the minus, plus, plus. All these rules are coming from your rules for the spinners you had, right? If I'm not wrong, the helicities.
You are absolutely right.
Yes. And the second question I have is like regarding the double copy thing which you mentioned, because in Yang-Mills theory, we also have these color factors which goes into it. So how does it get translated in the gravity sector?
Sorry, can you repeat the first
in the Yang
the question?
We have
in the Yang-Mills theory, we have
structure constants, right? And does it get simplified in the gravity sector as well when you square it?
That is a good question. In fact, I am not using here, for example, all the argument that people from Bernard Carrasco, Johansson, BCA, recursion relation use, where they, for example, imposed or found a connection between color terms in the numerator of the amplitude, and then they replace this with the kinematic term. We are not using that here, but let me show you here, for example, here. Are you able to see my screen still?
Yes, yes.
For example, here, this is the amplitude, this result. For example, you can see here, we have a squared plus p squared 2 times, but we have here this term. This F1, for example, take into account the color structure. This relation that I show you here was just between the kinematical structure. I'm not saying anything about the color. For example, here in the this is from gravity. For example, let me show you. Yeah, here. For example, here. This is the result for the gluons or photon. You can see here, for example, the electric charge. For sure, here we don't have electric charge in the gravity side, but the relation is just at the kinematical level at this moment in my talk. I don't know if this answered your question. So I'm not saying anything about, for example, about relation between color in the Young mills and another conserved quantities in gravity. It's just pure kinematical terms. That's why you still need here in this approach the Lagrangians, because you still need to put by hand the constant in the vertex of the Feynman diagrams, right?
Yes. Yeah. And I'm sorry, it was very quick for me. The beyond Einstein Hilbert action as well. Like, did you include non-minimal coupling for the Einstein Hilbert action? Well, yeah. Okay.
Yeah.
Thank you.
No, thank you. You can read more here in this. We already have it in an archive.
Sure. Thanks.
At least the first version.
Okay. Any other question? I actually have one, Bryan. It's you mentioned at the beginning, like the relation you can compute the 4-point function for graviton, starting from the 4-point function in QCD using a result from string theory, right? There's a connection that you mentioned that comes from string theory. And
yeah, that's right.
So from this point, all the following results that you showed us, do they also depend on string theory or on some ultraviolet? Which ultraviolet theory you're assuming is correct? This doubling, copy.
No, excellent question. No, this was, I showed this just as a motivation. Just as a motivation, a kind of philosophy or at least following this string theory philosophy teach us what to expect in our result, but our results are direct without any magic previous result from string theory. We don't use anything. Yeah.
Okay,
it's just direct calculation.
Yeah, I see. Perfect. Thanks. Okay, if there's no more question. Okay, let's thank once again Professor Bryan Larios. Thank you so much for your talk.
Thank you, guys, and congratulations for this amazing event.
No, no problem. Thanks you really.